Welcome to the fourth lecture of the fifth week, the machine learning course. This lecture will be about reinforcement learning. This lecture will be divided into three parts. So we start today with part one, the introduction. For the two first subthemes we have so far discussed this week, explanation-based learning and inductive logic programming. These approaches stems from a tradition of computer science and logic. What they have in common with what we're going to talk about today is that they learn not in a vacuum, just from a set of examples, but on the brink or border of a reasonably strong, already existing domain theory. Reinforcement learning, the topic of today, comes from another academic tradition. Actually, reinforcement learning methods, as they look like now, are very much inspired and have been growing out from a long tradition in control theory. But as for the other system we talked about, reinforcement learning is not learning in a vacuum. It's actually learning on the border of an existing system with an existing domain theory. The intuitive scenario for reinforcement learning is an agent that learns from interaction with an environment to achieve some long-term goals related to the state. And the state is the state of the environment, of course, also with the agent within it. So this iterative learning takes place as a series of actions on behalf of the agent and by a systematic feedback from the environment on each action. The mapping from states to possible actions, which means is actually what controls the actions in each state, is called the policy. The achievement of goals is defined by rewards or a reward signal, and those being the feedback on the actions from the environment. So this terminology is very important. Actually, it's highly recommended, I would say, in this area to try to really thoroughly learn the terminology, because these few basic concepts will come back in all kinds of forms when you look at very many different kinds of algorithms in this area. So, apart from reward, which is the atomic feedback on a single action, there is also another important concept, or two related concepts. So, in this area, a lot of the work is centered around not just a single action, but a sequence of actions. And a sequence of actions we typically call episode. And an important concept then related to rewards is the cumulative reward over a whole episode. So it's a sum, and not really a sum, because the way you aggregate the rewards can differ, but at least one can say it's the aggregated rewards over a whole episode, and that we call a return. And an action sequence then is the the set of actions from a specific state to something we call a terminal state. And of course this has to be defined from problem to problem, what means to be a terminal state. So the goal of most algorithms in this area is to establish a policy. This means a policy for an agent for how to act so that it maximizes the returns across all possible action sequences. And there are many examples today about reinforcement learning. Actually many success stories described. So on the front page you could see some slides referring to the AlphaGo system, which is one of the success stories where reinforcement learning implementation actually created a world champion level Go playing program. Also, there are other examples on this slide. You can see a small robot that should manage to navigate through a maze, assuming that this robot is provided with a reinforcement learning system. As I said, it's highly recommended to really learn the terminology for this area, because it will simplify all further work. So let's now again go through that term by term. So an environment here is a microworld defined for the particular reinforcement learning problem, including the agent. And many times when this is referred to, we use the letter E. Then we have an agent, often designated as A. A state is a particular configuration of the agent within the environment. And typically here we use the letter S to refer to it. Terminal states are defined end states for a particular reinforcement learning problem. So for every domain, the terminal states have to be clearly defined. And then we come to actions. So an agent selects an action based upon the current state and the policy P, which is had. And the policy P is a mapping from states of the environment to the potential actions of an agent in those states. So policies can be deterministic, which means that the policy depends only on S, or it could be stochastic, which means that the policy also depends on A. Related to that, there is another concept called transition probability function, which is actually a function from S and A onto a new state S prime. And this specifies the probability that the environment will transition to state S prime if the agent takes action A in state S. An episode, also sometimes called epoch, is a sequence of states, actions and rewards, which ends in a terminal state. And a reward gives feedback from the environment on the effect of a single action A in state S leading to S. Discounted reward is a concept that means that when we calculate, accumulate rewards over a whole episode, we want to implement some intuition that what we do early in the sequence have more weight than that we do later in the sequence. So therefore, we want to put a kind of discount factor on all on the later steps, the action steps in the sequence. So typically the discount factor lambda is a number between 0 and 1. The return is the accumulated reward over an episode. So finally then, the value function, or is the estimation of the value or utility of a state S with respect to its average return, considering all possible episodes within the current policy, ending as always in terminal states. So this value function must continually be re-estimated for each action taken. So finally, the model of the environment, to refer to two things already mentioned, is that the model of the environment is considered on one hand as the relation, the function t from S and A to a new state S prime, and the rewards associated with all those steps. To rehearse a little on the terminology, one step more, we introduce a little example called the 4x3 world, which is actually a little table, and it's a board of 4x3 positions indexed by 2 coordinates. So the agent has a start position in 1.1. The position 2.2 excluded. It's like it's forbidden. There are also 2 rewards. I mean, actually, there can be in reward for any step taken in this kind of domain. But in some domains, it's more common that you get a reward in the end. So maybe one can say there are 2 categories here. There are these kinds of domains where you get a reward when you reach the terminal state, or there are these domains where you get rewards more or less for every step you take. So both variants are possible. So here in this case you can see it's one position, 4.3, that has a positive reward of +1, and there is another one that has a negative reward of -1. Actually, there is no fixed rules for the ranges of rewards. So that can be, it's up to the designer and the design for a particular problem. So for reaching all other positions, give a reward 0. And the action is to move up, down, left, and right. Of course, the board as itself restricts what actions that can be taken. So the policy is deterministic, which was already I mentioned earlier here. So, and just to repeat it, it's determined in the sense that every action in a specific state can only lead to one other state. In the stochastic case, one action can lead to different states, and there can then need to be some probability for in which state the same action end up in. You can also see in this example some exemplification of what an episode is, and you can see what return those episodes gives in the end. I mean, here it's very simple because only the last step gives the reward. As I've already said, there is a strong inspiration on the area of reinforcement learning from control theory. So even if the definition or characterization of what reinforcement learning is has been developed within the machine learning and artificial intelligence field, the kind of the models used and the technique methods used bear a strong resemblance to those traditionally used in control theory. So therefore it's not surprising that the way of describing and modeling a reinforcement learning scenario is inspired by such one model coming from the control theory field, which is Markov decision process, that we here abbreviate MDP. So in a Markov decision process, we actually then have that kind of setup that we more or less already described for reinforcement learning. So we can say that an MDP is like a four-tuple of a state of states, actions, rewards, and transitions, where S is the set of states, A is the set of actions possible for each state that the agent can choose from, defined by a policy P. And then we have the reward function, which is there is feedback on each action leading to some other state. And then we have a transition probability function specifying all these probabilities from S to a state S given an action A. There is one thing that is important to note, that coupled to this model is this assumption that when we look at the probability, at the state probability, we can forget all the paths that led to this state. So the Markov property says that transition probabilities depend only on the states, not on which path that led to that state. So also in this kind of framework, we have the goal for all kinds of algorithm, which is to find policies P that maximizes the return, which is the expected future accumulated, possibly discounted reward for episodes starting from one state and moving to a terminal state. And to the right you can see an exemplification of this state transition where you see the probabilities, just an example of probabilities for a specific case. Yeah, and it's exactly the same example that we looked at, this 4 times 3 board example. So now it's time to come to a very important distinction for this area. So in one MDP scenario, I would say this default one, we have a complete and exact model of the Markov design process, in the sense that the transition function from states and actions to a new states, and the reward function from states and specific action are fully defined. So there is domain description available that can completely specify those two functions or relations. And so in this case, where we have complete knowledge available, the MDP problem is a planning problem. that can be exactly solved by use of, for example, techniques like dynamic programming. However, in many cases, these two relations, T and R, are not completely known. So this means that this information is not available from the domain, meaning that the model of the MD is not complete. And this case is that what we truly call reinforcement learning. That the complete case is more of a standard problem in control theory, which can be handled by standard techniques like dynamic programming, and is essentially a planning problem. While the case where we have not complete knowledge is a learning problem. As a reference point, let us first look into how the case with complete knowledge is handled, so that we have a reference point. So, as I said, the standard technique for handling this situation is called dynamic programming, which is an algorithm design technique for optimization developed by Richard Bellman in the 1950s. So, like divide and conquer, dynamic programming is simplifying a complicated problem by breaking it down into simpler subproblems in a recursive manner, combining the solutions to the subproblems to form the total solution. If a problem can be optimally solved by breaking it recursively into subproblems and then form the solution from optimal solution to the subproblems, then it's said to have an optimal substructure. However, there are other ways or methods for breaking problems into pieces, like divide and conquer, but in that case, subproblems are the problems are supposed to be totally independent. In dynamic programming, one can allow subproblems to be, to some way, in some sense, dependent on each other. So this way of thinking about reducing a problem into subproblems also affects the way we think when we want to estimate, for example, the value function or utility function of a certain state in a Markov decision process. So typically, we define the value function recursively in terms of the value function for the remaining steps of an episode. And also typically we do the same when we find a way of calculating estimates of the policy function needed. There is also an important equation that defines what is an optimal value function in this complete knowledge situation, and that equation is called the Bellman equation. Before we continue, I must tell you a funny story. Not so long ago, somebody asked me actually, why is this method called dynamic programming? And then I had to say, I don't know. Actually, I always accepted the name. I just know what it is. But then, because I got the question, I really tried to search for the reason behind the name. And then, funnily enough, I found this little piece from some old article where actually Professor Bellman himself in the 50s wrote that, the reason I worked on a project sponsored by the US military, and at that time it wasn't really popular to do something very theoretical if you had funding from the state, especially from the military. So therefore you always had to defend what you do, so it's useful for the purpose you were funded. So actually, as this story goes, Bellman chose a name that looked supposed to look very practical, so we couldn't be accused of doing something theoretical or too mathematical. So that explains why maybe this name is a little difficult to understand the relevance of. So the main principle of dynamic programming as a way to recursively divide up a problem in smaller parts and take the solutions to the smaller problem, to the subproblems, and combine them to the solutions of the larger. So this way of thinking also then affect the way one in dynamic programming plan the calculation of the various important functions. So as you can see here, there are two functions, the value function and the policy function. And both these functions are defined in a recursive way. So this means that the value function of a state S is actually the sum of all episodes starting in S. But of course, via different actions leading to other states as S prime. And actually taking the probabilities for going in these various directions, but for each direction, take the sum of the reward for taking that direction and add the discounted value of the value function in the new state. So you see, you start from the discounted value of the state you're going to, you add the reward, you multiply by the probability to get the full picture. And in a similar way you do with the policy function. The only thing is, for the policy function you want an advice on which argument to take. So therefore, logically, you look at the same kind of expression, the value function, but you want the argmax, which is the A that gives the position, the action A that gives the highest value of the value function, which is the reasonable action to take. But also this then equation have this recursive structure. Then we come to something called Richard Bellman's principle of optimality. So that says that an optimal policy has the property that whatever the initial state and the initial decision are, the remaining decision must constitute an optimal policy with regard to the state resulting. So whatever step you take initially, still in order to get something totally optimal, even the rest must be optimal. And coupled to that, we also then have the Bellman equation, which is an equation for specifying what could be an optimal value function. And as you see, for that, the structure of that also is the same recursive structure. Just because we, via the Bellman equation, have an equation that gives the criteria for finding an optimal solution, it doesn't mean that we have one. So what remains is to find methods that solves the Bellman equation. We don't have much time to go into this at this point. So on this slide, I roughly mention a few variant approaches. Something called value iteration, where we actually, through a simple procedure, iterate the values, or policy iteration where we do the same for the policies. Actually, it's always the case that if you have you can always infer one from the other. So if you have an optimal value function, it's pretty straightforward to infer an optimal policy function and vice versa. There are also other techniques you can use as linear programming, but we will not go more into this. I will now shortly introduce to you a simple example to illustrate the thinking of dynamic programming. So this is actually not reinforcement learning. It's just an example to illustrate the recursive style of reducing a larger problem to smaller problems and then combine the solutions. So this is actually a graph, and every edge has a value or a weight. You can say it's a distance here. So the task is to find the shortest path. And actually, as you can see here, one can easily see in this simple example, the shortest path is 9. But if you have a general problem, you need a method. And for example, if you have a greedy method, the greedy method always starts where you are and take the best choice locally, but never backtrack. So in this case, for a greedy method, you take 1 from S, you take the edge with weight 1, you come to A, then you take the edge with weight 4, but then when you come to D, you have only one way to go, and unfortunately you need to take an edge with weight 18. So then you are with a total of 23, which is absolutely not optimal at this point. However, what you can see on the next slide is that the dynamic programming approach is not greedy, it's rather more like breadth first. So actually what dynamic programming does is systematically in parallel checks all paths recursively, and actually dynamic programming in this case will, in contrast to the greedy algorithm, provide you with a good approximation. So what we will do for the rest of this lecture is that we will accept that for the case where you have full knowledge, you can use dynamic programming and techniques related to that. But for the other case, where you don't have full knowledge, you have to rely on other methods, or maybe reduce them to a problem where you have full knowledge, and then you can continue. So we will not make an attempt to generalize the Markov decision processes in a direction that makes them more useful to the case where you lack full knowledge. However, there are such extensions, and on this slide you can see one such attempt. So it's called partially observable Markov decision process. And actually, what the extension is very simple, but because you also introduce a notion of observation. So apart from getting a reward at every state, an agent also can make an observation, which is then a partial picture of the environment. Actually, it turns out, but if you introduce this, this kind of model is more useful also for the case with not complete knowledge. But for time reasons, we will not go into this sidetrack either. So this is the end of part 1. This is soon to be continued in part 2. Thank you.